Hello, so today we are going to talk about this problem, which is part of Leetcode Daily Challenge, maximum value of K coins from piles. So we have n piles of coins on a table, and each pile has a positive number of coins, and each value is a denomination. So for example, this means 1, denomination of 1, this means denomination of 100, and the array is represented like this, where the first element is the top of the pile. And you can choose any coin from the top of any of the pile you have. So you get the piles as a list, and the top is the first element. So for example, here, these are the 2 piles we have. And you can take only from the top of the file. So you can take 1, for example. But once you take 1, you can take the next on the top, which is 100. Same thing here, you can take 7. And the goal is taken from top to bottom from these piles. We want to return the maximum total values of coins you can have. Suppose you put these coins in your wallet, but you can choose only K coins, right? So you can choose only K. For example, in this first example here, you could choose only 2, but you can choose any. And so here, one option is to choose 1 and 7, but that will give you only 8. The other option is to choose 7, and then the top of the pile next is 8, so you get 15. But the most optimal one is to actually take 1 here and then take 100, so that would be 101. So that's the problem statement. Now, let's see how we can tackle it. Okay, so how do we tackle this? Well, the first thing to think about is from the first example we saw in the description. There is not really a good greedy approach, because, for example, this example is like this. We have these piles. This 100 being here makes it tricky, because you can't just take the max from the top, right? If you take the max, then you'll take 7, and then the next max would be 8, and so you'll end up taking 8, and so it would be 15. So you can't really do that. There is not really a good heuristic we can apply. And so whenever we have that situation, we should think about maybe using dynamic programming or some sort of backtracking, because those you could just try all possibilities, all choices. Okay, so that's the first thing we established. So if we want to try all choices, what would be what do we need to, what are the choices we have? What do we recurse on? Well, in this example, we just have 2, but we could have multiple piles. Like it can be up to, I think, the number of piles can be up to 1,000, right? And so you could have multiple, but what would be the choices we have? Well, each time we have the choice of which pile to take from. So I for pile to take from, and how many to take from of pile. Now, this how many is interesting, because, okay, actually before doing that, let's just say we need to know which pile and how much is remaining, because once we take, let's say, this 7, then we only have K equal to 1 remaining. So each time we need to know how much is remaining to take, so that we can know how much to take. And so we need to know the remaining value of K. Okay, so we can first use this as our state. So let's try it. So let's say, for example, in this here, the first state is we try with pile 0, and let's say we have still 2 remaining, right? And so in that case, well, we could try with pile, we could start with pile 0, and from here we could choose either to take from pile 0 or not to take. So those are the choices: take or not take. There is really no other option. And so if we take here, then we'll take from pile 0, right? And let's say we would have only 1 remaining, right? Okay. And the other choice is to not take at all from pile 0. Is just look at it, not take, go take from 7. And so go take from pile 1. And so we take from pile 1 with 1 remaining. Okay. And then if we had other piles, we will just continue the branching here. And now here, from this one, once we take 1, we could also decide to keep taking from 1, which means taking this 100. And so in that case, we will take from 0 again and have 0. Okay, but what's missing? Well, we need to calculate, what we want is to get the max value, right? The max total coins we take. And so with recursion, we can just return that up to our caller. And so here, what do we return to our caller? Well, we return the coin that we just took, which is 100. And then here, what do we return? It returns the max for all of its children, right? And so here, what are other options? Well, here, the other option is to go and take from pile 2 here, pile 1. And so in pile 1, we take, and so if we take from pile 1 at this point, well, we take 7. And so here we return 7. And so this one checks which one is the max. And so it returns 100, which is because it's better. And so this one returns 100. But since here we take, so here we took from pile, we took the first one, we took 1. And so it adds it to whatever the max is from its children. And so 100 plus 1, that's 101, and it returns it to the parent. Okay, so let's continue our branching here. And so here, 1 and 1, we took from 7. And so we have 7 here. And then we have 2 choices. We can either take or not take, right? And so not take would be problematic because we have no other pile to take from, but let's just write it again. So here would be take from pile 1. We can't not take because there is no other choice, but here we can take from pile 1, and now we have remaining 0. And so now what should this return? This one, we are still on pile 1, but we have nothing, we have still 1 remaining. And so this one sort of needs to return 0 because we reached the end of our piles, but we still have remaining not equal to 0. And so here it can return 0, but here we would return taking 8, right? So here we took 8, and so we return 8. And then this one takes the max, which is 8, and then adds itself, which is 7, and so it returns 15 to the parent. And now the parent compares 101 and 15, and so it returns 101. And so you can see with these choices, also the other thing you notice is that some of them are repeated. So for example, here 1 0 is repeated here. And so we will need to do a memoization so that we don't recalculate things. But this is roughly the idea, is that each one has just choices of take or don't take. And take would be, let's call our function maybe just a helper function. What does not take mean? Well, not take means just skipping and going to I plus 1. And the remaining coins to take would be the same. So this is not take. Now, what does take mean? Well, take, we have multiple options. We can either take just this one, or continue along the path and basically take 2, or continue along the path and take all of it, right? And so we have the choice to take from 1 to the end of the pile, okay, so what does we can take all of so how much is that? How should we try that? Well, we could just do a for loop, right? And the range would be the length of the pile, right? And the pile is at index I, right? But the other thing is that we don't need to take more than the remaining k coins, right? So let's say, for example, here 2, we don't need to take this 3. We should take only up to 100. And so we need to take the min between this and k. Okay, and then now we can take it. And so taking it would be taking up to j, right? And so that would be, we will need to have the sum. So we will need to have some current value here that calculates the sum up to j. And so here we'll add for pile I at j. So it calculates the sum to up to j, but once we take, let's say 2 or 3 from this pile, we can go to the next pile. And so we go to the next pile, and the remaining k would be, since we took here j plus 1, because the index starts from 0, we took j plus 1. Okay, and so the remaining k will need to be reduced by j plus 1, and so we just subtract j plus 1, which will be j minus j minus 1. And so this current would be what we need, what would be the total. And so we need to, since we want the max of all children, that means we need to have some sort of result here, that first we take this one, and then we take the max out of all the possible choices here of res and this choice here. So that's the idea. Now, one thing I want to mention is that you may say, why not just take one and go here? Just take one each time. Well, the problem then is, well, you would have, once you take 7, the other choice is to take 1. Let's say if k equal to 3, you can take 1, take 7, and then go back and take 100. But why do the go back? Like, the order doesn't matter. Just take 2 here and then take 1 here, and that would be the same outcome. So that's why we are doing this for loop here. Okay. Yeah, so that's pretty much it. The idea, we can just use this recursion and then do all the choices, take the max, and we can memorize the result here. Okay, so let's code this up and make sure it passes. Okay, so let's implement the solution here. So what do we need? We need our helper function first. That just, we said the state is the remaining values of k, the remaining coins to take, and I is the index of the pile we are considering. And what we need to call it with, well, we start out with the first pile and we have k coins remaining. And so we said the choices are either take or don't take. And so we'll start out with don't take, and then the second option is take. Okay, so don't take is easy because we just go to the next pile and then we didn't take anything, so the remaining coins are still the same. And so we need to have a result that we will get the max with take, and then that's what we return at the end. Now here, what would be the max? So we have res equal, and the max would be between that and what? We said we need to take, but we need to consider taking as many elements as we can from the pile because we don't want to go back to it. And so we want to say j in the range of as many as we need. What's that? Well, that's, we could try taking 1, try taking 2, and let's say we need only 3. Well, try taking up to 3 if, of course, the pile has at least 3 elements, okay? And so that's why we take the min here of the length of the pile at I, of course, and we want to take the min of that with k, the remaining k, right? The remaining coins we need. Okay, so when we do that, well, here we need to also keep track of how many, keep track of the sum of up to k pile I. Well, we could do, of course, just like, to get that, we could just do the sum, right, of piles I, j, right? Or maybe, let's call this x, for x in the range of k, in the range of j, right? Because that's taking the sum for all the piles, the pile values for the piles I up to j. But instead of doing this sum, which would be another, like, of the length of the piles I iteration or operation, we can just keep a cumulative sum for that. So what does that mean? We can just start with current equal to 0 here and just keep adding the value for piles I, j. So first at 0, this would contain just piles I at 0. When we are at 1, which means we want to take up to index 1, then this will contain piles I at index 0 plus piles I at index 1, which is exactly what we want. And the same thing happens for index 2 and index 3, okay? So we can actually just rely on that. And now this would be current plus this, right? Because we make the choice, we take up to j, and then we go to the next pile. And what's remaining for the coins we need? Well, we already took up to j. And since j here starts at 0, we can just subtract j minus 1. Okay, and that should be it. Now, now we need our base case. What's our base case? Well, the first base case is if we reach the end of the piles, right? There is no more piles to take from. We already tried all of them and tried taking as much as we can from each pile. And so in that case, we want to return 0. Now, what is the other case? Well, if we took all the coins we need, we should stop. So if this remaining k is equal to 0, that means we took all of them, then we should return 0 as well because we stop there, and this will take care of taking the max. Okay, so now let's just run this first on the first set of examples. We will still need to memorize, but it looks good, so let's add our memorization. So we just need a small map here, like this, and then we can just check if the state here was already added to our map, like this. If it's there, we can just return it like that. If it's not, then we want to calculate, and then at the end we want to assign this to res. That should be it. Let's submit. Okay, so that passes and it gets accepted. Now, what is the time complexity here? Well, let's see what are the states we have. So I can go is the length of the pile. So let's call that length of P, the piles here, or length of the piles. Now, what is rem k? Well, that's just k, right? And so at least this function, we know it will run k multiplied by the length of the pile. So let's call the length of the pile here just p. So we know at least the function will be called calls, okay, this number of times, because we memorize it will never it will never calculate more than this, because if it exists already in the memo table, we'll just return it, okay. Calculations here, okay. And now what about this loop here that we are doing internally? Well, this loop goes for j, which goes up to the min of these two, okay. And so let's just say this is the min of the length of the pile. So what would be the max? So this would be the max of the values in each pile, and k, okay. And so what's the highest value for this? Well, it's just up to some, right? And k can be up to 2000, so it doesn't matter which one we take. So we can take, for example, this is just the sums of the piles, or the length. Let's call this the length of all piles, okay. So sum of length of all piles. So that would be then we will need to multiply this by that, and so here we have multiplied by this, okay. Let's call this s, okay. Let's call this last one s. So this would be p multiplied by k multiplied by s. Now what is this p here? This is just the number length of the pile, and here we have the sum of here we have the length of each pile, and so basically this is the total sum of all piles. So p multiplied by s here is just sum of all piles values, okay. Let's call that s. Let's call that x here, and so this would be just that x multiplied by k. And now if we take a look here, that sum of all the piles values is 2000, and k can go up to 2000 as well. So it should be fast. Now in terms of space complexity, we are mainly using this memo table or memo hash map, and so the values are a and the rem k, and so this is I here is just the length of the pile by k. So pretty straightforward, just the number of piles multiplied by k. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you in the next one. Bye.